The game of Towers of Hanoi consists of 3 poles and a certain number of discs, where each disc gets smaller and smaller in size. To start the game, all of the discs are placed on one of the poles. Now, your goal in the game is to move all of these discs to another pole. However, there are a few rules to follow. First, only one disc can be moved at a time. Second, a disc can only be moved if it is the uppermost disc on that stack. And third, no larger disc may be placed on top of a smaller disc. Let's imagine there was just one disc at first. How many moves would it take to move that one disc over? Well, it's pretty obvious, right? It's just 1. And we can record it on this piece of paper. So the number of discs, that's just 1, and that would just be 1 move. Now, what if there were 2 discs? Well, I think it's still pretty obvious, right? It's just move the first disc out of the way, move the base, and then move it back on. So we can record that on this piece of paper again. Now, what if there were 3 discs right over here? Well, it's still pretty easy, but is there a better way to do it? The answer is yes. Let's think about it this way. The first step we gotta do is to move the top 2 discs to another pole. Let's move the top 2 to B. And that takes 3 moves, because we've already calculated the number of moves it takes to move 2 discs, and we recorded that on this piece of paper. Now, the second step we gotta do is to move the base over, and that's just 1 move. That's pretty self-explanatory. And then the third step is to move the top 2 discs back on to the first disc right over there. And if you think about it, it's really just the same number of moves it takes to move this from A to B, right? It's just the same moves, but in reverse order. It's symmetrical, so it's still 3. To summarize that on this sheet, N3 would actually just equal to 3, because that's the number of moves it takes to move 2 discs, plus 1, that's the number of moves it takes to move the bottom disc over, plus another 3, which is really just 2 times 3 plus 1, which equals to 7. So if we keep on using this little trick here, if we have 4 discs, the first step, move the first 3 discs. Second step, move the bottom disc. Third step, move the top 3 discs over again. N4 would exactly be 2 times the number of moves for 3 discs plus 1, which is really just 2 times 7 plus 1, which equals to 15 right here. And this equals to 7, by the way. So I think you see the pattern here. As we add more and more discs, essentially the equation would be n of x would equal to 2 times n of x minus 1 plus 1. Now, this little equation is helpful. However, it's not helpful if you don't know the number of moves for the previous disc, right? So how about let's try to get this into something a bit more useful. Now, notice the numbers on the right here. If we add 1 to each of them, then 1 turns to 2, 3 turns to 4, 7 is 8. Realize that this is 2 to the 1. This is 2 to the 2. The pattern here is that n of x is just 2 to the x minus 1. Now, I want to show you a more visual way to do this. Let's just start with 1 disc again. We can move it to either B or C. And now it's starting on A. So we have A here. We can move to either B or C. And from B and C, it can move across from each other. So we can also connect these. Okay, so now let's do that with 2 discs. They both start at A, with the first one representing the first disc and the second A representing the position of the second disc. So from here, the first disc can move to either BA or CA. And from here, they can, move in between. So you can connect this. And I'll just fill out the rest of the chart here. Essentially, over here, these are the 2 answers, and the shortest route to these answers are these lengths. Now, I think you might see the pattern here. It's a Sierpinski triangle. And notice that there are 3 main triangles here that are all connected by these little, bridges. And essentially, in each of these small triangles, you're solving a mini 1-disc problem. Because here, the base stays the same. It's just the first disc that's moving. Same over here. And in between, you're changing the position of the base. It's the same concept with 3 discs. It's another bigger Sierpinski triangle in which we can see the multiple subproblems. We can see that there are 3 large triangles over here. And these are essentially all mini 2-disc problems with these little roots connecting them, where the largest disc will switch bases. And then in each of these little triangles, we have the 1, 2, 3 tiny triangles, which represent one disk problems, right? So as we progress higher and higher with the disks, it's essentially the same problems that are just repeating in themselves. From this visual method, we can not just see that n of x equals to 2 times n of x minus 1 plus 1, but also we can see that this actually equals to 2x minus 1. Because if you look at these points right over here, they double after each progression of the Sierpinski triangle. So for the first progression, there's 2 points. Second one, there's 4. Third one, there's 8. But notice that this is just 2 to the power of 1, 2 to the 2. This is 2 to the 3. And this number right here, the exponent, is exactly the number of disks we are trying to use. So if we're looking at any of these examples, it's always 2 to the power of however many disks there are minus 1, because we're trying to find the intervals in between. So that's why it makes sense that these two are equal to each other.